Okay, so this is going to be an instruction video on how to do problem 10 from the homework. So problem 10 is a problem asking about the net force on three different charges and the net force from the charges acting on each other. So the way we're going to do this is we're going to calculate the net force on each charge. Well, calculate the forces on each charge, sum the forces, and then determine the magnitude and direction. And the way we calculate the forces is by using Coulomb's law. And remember that Coulomb's law is the force equals K, which is a constant, times Q1 times Q2 divided by R squared, where R is the distance between the two charges. So we're going to start with charge number 1. The first positive charge on the left, which is 70 microcoulombs. So, as we can see, there is a positive charge over here, which is acting on charge number 1, and it's going to be a force in this direction. We already know because they're two positive charges, so it's going to repel it. However, there's a negative charge over here, which is going to create a force in the opposite direction on this charge number 1. This is a force due to 3 on charge number 1. That's what that means. And since these forces are in opposite directions, the net force here is going to be the difference between the two. Now, remember that it doesn't actually matter whether we're subtracting this from that or the other way around, because in the end, we're just going to call it positive and then assign it a direction, either to the left or to the right. Just with common sense. So what we're going to do is just basically plug and chug it into Coulomb's law. So here we have K, 9 times 10 to the 9th. Then we have the two charges. This is charge number 2, which is 48 microcoulombs, and charge number 1, which is 70 microcoulombs. And the 10 to the negative 6th is the micro. We have to use coulombs, so 10 to the negative 6 is micro. And then down here, we have R, which is 0.35 meters, which was given, squared. And that equals 246.9 newtons. And then from that, we will subtract the other force, which is force number 3, which is negative 80 microcoulombs. Now notice I didn't put the negative in here. And if we go back to where I wrote Coulomb's law, I have absolute value signs over here. And that's just because this force is going to be positive in the end, and we're just going to assign it a direction with our common sense. So it's just, I'm not going to put the negative in here. And also notice down here, we have the distance between the two charges. We can go, the distance between these two is actually doubled because, well, not in this picture, but whatever, is twice as much as this in the original problem. So that equals 102.9 newtons, and the difference between those two is 144 newtons. And we can see that the orange is bigger than the blue, so that means the net force is going to be towards the orange, so towards the left. So that the net force is going to be to the left, and that's charge number 1. Charge number 2 over here, this one, we can say that the force from charge number 1 on 2 is going to be to the right because they're two positive charges and they're going to repel each other. However, there's a negative charge over here, and this is charge 3, so that the force of charge 3 on 2 is going to also be to the right because it's positive and negative and they attract. So we can obviously see that this net force is going to be to the right. So it makes it a lot easier, and we just add the two forces together to get the net force. So what we're going to do is just plug and chug into Coulomb's law. We have the charge of number 1, charge number 2, and the distance between them, squared, and of course K over there. And that's 246.9 newtons. Add it to the force from charge 3 on force on charge 2. And as you can see, the 2r squared here is the same. That's because charge 2 is in the middle of the 2, so the r is the same on either side, obviously. So now to that we get 529 newtons to the right. The net force is to the right. Now, the next one is charge number 3. And this force is also easy to determine which way it goes, because it's going to have an attractive force on it from both of the 2 positive charges up here, because it's a negative charge. So this force is going to be to the left, which makes it similar to charge number 2, the way we did it, because we can just add the 2 forces. And you might think that we're going to report this answer as negative because we reported the answer to charge number 2 as positive, but we're not, because force isn't really negative. So we're just going to specify the direction by saying it's going to be to the left instead of calling it negative, because that's confusing. So anyway, we just plug and chug again into Coulomb's law. We have K, the 2 charges, and notice again I didn't put in the negative 80 because we know that it's not really, because we don't want that to be a negative force. So we just leave out the negatives until we get to the end. And notice also here I've doubled the distance between them again because it's a distance between 1 and 3, and they're farther away. And we add these 2 forces and we get 385 newtons, and this is going to be to the left, net force to the left. And that is all the question was asking. Thanks.